This is the brief on vector calculus identities. So what are we talking about here? Well, these identities are basically the mathematical rulebook. They're what connect the tiny, invisible dynamics of forces, like gravity or fluid flow, to the massive, predictable physical laws we can actually observe. First, a couple of the most fundamental identities are guaranteed as long as a vector field is, well, mathematically smooth. If the partial derivatives commute, meaning the order you differentiate in doesn't matter, then two things are always true. The curl of a gradient is zero, and the divergence of a curl is zero. This basically means that fields from potential energy, like gravity, just can't have any inherent spin. It's a mathematical lock on the conservation of energy. Second, these operators act like a bridge, linking what's happening at a single point to the whole big picture. The divergence theorem, for instance, tells us that the total amount of a source or sink inside a volume, that's what we call divergence, has to exactly match the total flow or flux escaping through its boundary. In the same way, Stokes Theorem connects all the microscopic rotational spin, the curl, over a surface to the total circulation you'd measure along the edge of that boundary. And finally, these operations let us neatly classify real-world forces. If a field has zero curl, we call it irrotational and conservative, which is a perfect description of gravity. On the other hand, if a field has zero divergence, no sources, no sinks, we call it solenoidal, and that's the precise mathematical language for things like magnetic fields. At the end of the day, these identities are the essential tools physicists use to translate complex dynamics into predictable physical conservation laws that govern everything.